morning to one and all present here. On behalf of R.M.K group of institutions and Binghamton University of USA, we welcome you all to the International Seminar Series on Introduction to System Science and Overview of Machine Learning and Artificial Intelligence. First, I would like to welcome our guest, Professor Hiroki Sayama, Department of System Science and Industrial Engineering, New York University, USA, for his gracious presence here. Welcome, sir. Next, I would like to welcome Dr. K. Chandrasekharan, Dean, R.M.K. Engineering College, who made this program come true today. Welcome you, sir. Next, I would like to welcome Professor Nagada, Department of Mechanical Engineering, CEG, Anna University. Welcome you, sir. I extend my warm welcome to all the participants from various institutions. Finally, I would like to welcome all the higher education coordinators of R.M.K. group of institutions. To say a few words about the seminar, in today's heavily interconnected world, there has been an increasing demand for professionals who have strong systems thinking and problem-solving skills. In this presentation, an overview of this very unique academic field that offers students with a wide variety of career options in STEM and other domains with several application examples in pandemic responses and other projects done by graduate students in their university will be highlighted. It also focuses on overview of artificial intelligence and machine learning. Artificial intelligence and machine learning have recently become very popular standard methods for data science, business analytics, and decision making in a wide range of application domain. And I assure it's going to be an interesting and informative session. Once again, I welcome you all. Welcome.
Thank you, ma'am. Now I request Dr. K. Chandrasekhar, Dean, R.M.K. Engineering College, to introduce our chief guest. Please, sir.
Good morning, ladies and gentlemen. It gives me great pleasure to be back here in the CEG campus in some sort of a capacity. I'm walking down the memory lane whenever I enter the portals of Anna University. And I should thank Professor Nagarajan, my former colleague, for having helped me a lot. It was by accident I met him the other day, and then that culminated in our getting this hall and then getting all the needed help from here, including the participant. Thank you very much for being here. Before I introduce Professor Sayama here, I would like to say a few words about what are the intention behind such seminars and other things. Essentially, all of you might have heard about this from many people and you must have read in the magazines and then papers also. The time we are living now and the world where we are living now, they call it as a VUCA world, VUCA world. V is for volatile, U for uncertain, C for complex, and A for ambiguous. So it's a highly volatile, highly ambiguous, complex, and totally uncertain period that we have been here. It has been there for the past about 10 years, especially after the advent of this sort of globalization, free trade and all those things. There were lots of benefits that came. There were also side effects which were very, very damaging. So nobody is sort of sure. And when you come here as students to engineering college, we pamper you by simplifying things. Professor Nagarajan will always say, everything is a sort of, a continuous system governed by very well ordered mathematical equations which have unique solutions. There's none of that sort, and they are all deterministic. Life is stochastic. High amounts of probability are there. And nothing is continuous. Everything is an assemblage of discrete elements. So, if you look at it and then we say it's a highly linear world, it's not at all. Every small step you take, there is an absolute non-linearity occurring. And then when we train you to be engineers of tomorrow, we put everything into the basket and say that life is simple. You have a wonderful time ahead. There's nothing like that. The moment you go out into the world, you are thrown into this chaotic world. So as an engineer, our duty is to train you to acquire problem solving ability. No problem comes with well-defined solutions or well-defined inputs. And then nothing is constant. Every model that you can make of life or whatever part of life there is, they are highly what you call as an initial value problems along with the boundary value problems. We ignore the effect of initial value and then assume that they are boundary values. It's not like that. And then in the greatest problem with the initial value problem is that we do not know what are the initial conditions. In life, you don't know it. And any small change in the initial value assumption will either lead you into a chaotic world or a highly stabilized world. And we totally neglect it. Such seminars, when we bring people with considerable experience or knowledge, they bring the actual realistic world before you that gives you some idea about what you are letting yourself in for. So that is a major idea of bringing experts from various parts of the world so that we can gain some knowledge about the real world. Otherwise, what we teach you is highly theoretical, and some of them are really horrible theory, like my friends here from Guindy Engineering College was saying that, like your finite element analysis. So, it's unfortunate, but we are guided by people like Professor Sayama. So, that is the idea of bringing in all these people so that we can gain by their experiences. I am very sorry that we are unable to make use, your students were unable to make use of such presence here, but we will keep doing. Anyway, we are recording it, it will be in the YouTube, so it will be available for all the students whenever they are inclined to view the YouTube. Now, it is my very pleasant privilege to introduce our chief guest today, Dr. Hiroki Sayama. He is a professor in the Department of Systems Science and Industrial Engineering and the director of Center for Collective Dynamics of Complex Systems. So he will take you into that VOCA world. And then at the Binghamton University, which is a state university of New York. Sunny is well known. It is located in Buffalo, which was very well known, in Albany and in Binghamton. I think there are a couple of more campuses, I think, which I really do not know. And he serves as a non-tenure track professor in the School of Commerce at Waseda University, Japan. School of Commerce at Waseda University, Japan. This is another message I want to send you. We have now started moving over from so-called disciplinary approach, discipline-based approach. Earlier, we forayed slightly in the border areas, we call that as interdisciplinary. Now we are foraying deep, we call it as a transdisciplinary. Today, you are not a full engineer if you do not have a knowledge of everything, something of everything. Then with some focus on that. So, any idea of the so-called major, minor, honors, whatever it is, they all stem from that fact. So, you can see that he is a living example of that. He teaches in the Commerce University there, apart from being an engineer, as well as an external faculty member of the Vermont Complex Systems Center at the University of Vermont. To highlight a few of his credentials, he received his BSc, MSc and DSc in Information Science from the University of Tokyo, Japan. He did his postdoctoral work at the New England Complex System Institute in Cambridge, Massachusetts. His research interests include complex dynamical networks, human and social dynamics, collective behaviors, artificial life chemistry, interactive systems, and complex systems education, amongst others. He is an expert on mathematical and computational modeling and analysis of various complex systems and has published more than 200 peer-reviewed journal articles and conference proceedings. He has written and edited 14 books and conference proceedings about complex systems related topics. His open access textbook on complex systems modeling and analysis has been downloaded more than 70,000 times globally and has become one of the standard textbooks on this subject. He currently serves as a board member of the Network Science Society and the International Society for Artificial Life, the chief editor of Complexity, published by Wiley, the founding co-editor-in-chief of Northeast Journal of Complex Systems, and an associate editor of Artificial Life, published by MIT Press, and as an editorial member of several other journals. We are happy that such an eminent personality is amidst us to give you a glimpse. This is only throwing an introduction. It is not leading you. We are going to follow up with very, very focused series of seminars on these emerging topics in the coming months. So we will inform you. Mostly we'll make them available on the YouTube also, but you can have interaction directly with the concerned people from various parts of this country. And we hope to sort of continue this service to the education in a small way. And thank you all for being here. I'll leave it open to Professor Sayama and to the compare. And I would like my good friend, Dr. Nagarajan, to say a few words.
Professor Hiroki Sayama from Binghamton University, USA, my mentor, and I have the privilege of saying that my dear colleague, about 20 years back, Professor Dr. K. Chandrasekharan, faculty members from R.M.K. College of Engineering, my dear student friends, I am very happy to be here this morning to say a few words. I think Professor Chandrasekharan has given the insight on what are the advantages of attending such type of seminars. And I always used to say, whenever I see the youngsters today, I wish I should be today's students, because of the reason a lot of technological developments are happening. Just to give an example, I like anybody else, I used to be very fond of James Bond movies in 1980s. I graduated during 1985, and in those days, James Bond movies used to have a lot of technological advancements shown there. It used to be very fictional, this thing. But whatever I saw in those James Bond movies, I work in an automotive area, and today I see all those technologies live on roads. Not only in the case of automotive, but also even in other sectors like aerospace. And today, if you look at it, I think the systems engineering in general, I'll put it, I think Professor Casey has given a good intro about the various subjects. Systems engineering is going to drive the world. Like today, if you look at it, we talk about robotics and automation, digital product design, digital manufacturing, virtual reality, augmented reality, Verilog systems. Then we have blockchain technology. Now, if you look at all these things, you will find that it's the artificial intelligence that plays a very vital role. Just to give an example on artificial intelligence for the students like you, I don't know how many of you heard about this Alexa. Have you? Okay, which can recognize a voice, wherein you can register your voice. You just say you don't have to turn on your lights and fans on or off. You just give a command to Alexa stating that put up the lights, put on the fans. It'll do it. You don't have to put on the system. If you want to play music, yeah, you can just command. I want English music, I want Hindi, Telugu, Tamil, whatever. So this is a live example of artificial intelligence. So coming to the virtual reality and augmented reality, again, if you look at the virtual reality, it is 75% virtual and 25% real. But whereas if you look at the augmented reality, it is 75% real world situation and 25% it is virtual. Just to give a good example again, if you look at the cricket, I think that's one of the popular sport in India, most of the youngsters like today. And in those days, we used to have only two umpires, namely the main umpire and the side umpire. Okay, either any one of these two will take a call in stating whether the player is out or not. But today the situation has changed where we have a third umpire, right? Where we have cameras, close monitoring systems, and they zoom in and to see whether the batsman has reached the crease before the ball knocked off the bails. You might have seen that, right? So this is a good example of augmented reality. Big data. Today you talk about so much about big data by the computer science people, right? So what is that we are talking about big data? If you take the case of Boeing 747, it has only 10 million source of lines of codes. But whereas if you take the case of the modern day automobiles, it has about 100 millions of lines of code. So you can imagine what kind of a data that needs to be generated. And we talk about autonomous vehicles, connected vehicles in the US, right? And a lot of data needs to be generated. So we talk about big data. So what I am trying to conclude here is that, you guys, because you are the future of the country, right? Wherein you're going to see a lot more technology. So whatever technology that we had seen during the last 10 years or so, and about 30 years back, they predicted that, these are the technological options that we are going to have in the future. But after 5 years, we do not know what kind of technologies that we are going to have in many sectors. No, this is where you find that, as rightly put forth by Professor Casey, that we have moving from interdisciplinary to transdisciplinary. No more you can say that I am a mechanical guy, so I can work only in mechanical area. Or I am an electronic guy, I can work only in electronics area or computer science. Now today, I always used to say, if you take the case of an automobile, we need mining engineer. Because you need to get materials for making the automobile components and parts. We need electrical engineer because we have a lot of electrical systems there. We need electronic engineers, we have a lot of electronic gadgets there. We have sensors, we have actuators. Then, today if you look at an automobile, you will find that about 50% of the manufacturing cost goes into software alone. Right? So we need to have the software or the computer science or the IT engineer. Like robotics again, it's highly interdisciplinary. So like this, so what I would suggest is, as engineers, if you're a mechanical engineer, you need to know some fundamental, like as rightly put by Professor Casey, that you need to know some fundamentals about the software, some on electrical, some on electronics. Likewise, the mechanical and other students should understand what is the mechanical system, because though we will have all these AI applications and things like that, but still you can't do away with certain mechanical systems. You need to have motors. Maybe you can have intelligent motors. How you make them as intelligent motors? You have more of senses. So in this way, you find that it is going to be, the future is going to be highly challenging, right? Unless you keep abreast with the technological developments that are happening around the world, you won't be able to sell yourself in the market. Okay, with these few words, I wish you all the very best, and I would like to thank Professor Casey and the organizing committee of this seminar for giving me an opportunity. It's really, I was very much thrilled when I was asked to, chair the dais with Professor Casey and Professor Sayama. So thank you very much once again.
Thank you, Dean sir. Thank you, Professor sir. Chief guest Dr. Hiroki Sayama, Professor, Department of System Science and Industrial Engineering, Binghamton University, USA, to take over the session. Please, sir.
Good morning. Okay. Thank you very much, everyone, for being here. This is my great honor to have this opportunity to share some of my experiences. And I would like to thank everyone, every individual who made this possible, led by Dr. Dean Chandrasekaran and many other people at the R.M.K. and Anna University. Thank you very much for this opportunity. Let me start by introducing myself. As Dean Chandrasekaran mentioned, my career path has been very, very messy. I obtained my, hold on 1 second. Is it working? Yes. I obtained my PhD in computer science back in Tokyo, but since then, my career has been everywhere in the academic and professional field, including complex systems. So this is the highly transdisciplinary research area that studies many different components working together. And then my first academic appointment was at the Department of Human Communication. A lot of the social components are there. And then I moved to Binghamton University in 2006. My first appointment was in bioengineering, even though I have no formal training in biology or engineering. That's a weird thing. Anything that relates to computers, mathematics, you can move into pretty much any kind of discipline. I am now at the System Science and the Industrial Engineering Department at the Binghamton University, and also I have the additional affiliation with the School of Commerce at Waseda University in Tokyo. So this is one thing I would like to illustrate. Many of the students attending here in person, as well as watching the live or recorded lectures online, they probably have a very strong background in computers and mathematics. Please keep your perspective very broad. You have a very strong skills that can be generalizable to many other domains. So don't just imagine that getting the IT industry is the only way to develop your career. Instead, you can move into many, many different possibilities. So today, the official title of this event is called Introduction to System Science and the Overview of AI Machine Learning. I'm going to go backward. So I will structure this lecture series in 3 parts. First, I'm going to talk about AI and machine learning because I know many of you are interested in that topic as an entry point. And then I want to give some intermediate lecture connecting AI and machine learning and what is missing, at least from my perspective, in the current trend of AI machine learning that actually nicely connects to the systems modeling, system science. The last part of the talk will be about introducing ourselves, who we are at the Binghamton University, what kind of academic program system science is. And then some of you might consider coming to Binghamton. We'd like to welcome you if you plan to study in the United States. So that's my plan. And between those 3 shorter lectures, we'd like to have a short break so that you can come to me and ask a question if you want. Right? So let me switch to my slide. Okay, so let's begin talking about AI and machine learning. It's a fun topic. Everybody wants to learn, and I assume that not so many people here watching this lecture are experts of AI and machine learning. So please don't worry. This is not going to be a technical talk because, to be honest, I'm also not the researcher working on the AI and machine learning themselves, but rather I'm also the user of those. So this is more or less just a quick overview of what kind of concepts, topics, tools has been developed in this field. And sometimes this field can be very intimidating. This is the image I took from some of the blog posts in Medium. There's so many concepts, keywords discussed by tech-savvy people, And as a first-time learner of machine learning AI, this can be very confusing and intimidating. So my objective in this initial lecture is to give you a landscape. It's a map. So you can just make a connection between someone saying something and some concept you already know. That's a plan. And I have already shared all the presentation material for today with Dr. Uma, so she will share the link to the Google shared folder with all of you. So you will have access to all the presentation material later. So here's the overview. I would like to talk a little bit about the history of machine learning and AI, because this has a very, very, very long history. It's not a new thing, in my opinion. There are ups and downs in this field, and then I'm going to talk about some of the key ingredients of all kinds of machine learning AI has. One is basic statistics. So statistics now has become the foundation of almost any kind of scientific effort. I'm sure some of you, many of you have already learned statistics. Believe it or not, you have already have the foundation of AI machine learning. Sometimes some of the statistical concept has been just renamed with cooler names, but essentially the modern AI machine learning is still doing the basic statistics. The second ingredient is optimization here. So this also has a very long history, more than hundreds of years of history. So those two, stats, optimization, form the basis of any kind of machine learning and AI. And then I'm going to talk about the artificial neural networks, deep learning, and some of the modern issues. What are the current problems, challenges in this area? Because there are still so many unsolved problems, even now at the time of 2022. It's good to know what is not possible in AI together with what's possible, so that you will have the future career path, possibly you can move into solving those challenges. So that's a plan. Okay. Let me start talking about this person. I hope many of you know who he is. Raise your hand if you know him. Okay. Anybody who is majoring computer science, you should know him. Alan Turing. He is my big-time science hero. He proposed a concept called the Turing machines. That is the theoretical basis of all kinds of computational devices we are using. And later, he also worked on the highly classified tasks to break the Enigma code. That's encryption used by German military system. And thanks to his contribution, millions of people's lives have been saved. And then World War II ended, estimated by 2 years, thanks to his contribution. This actually became the movie, The Imitation Game. Have you watched this? Raise your hand if you have watched the film. I highly recommend it. Yeah, thank you. So some students watched it. 2014, The Imitation Game, the Academy Award-winning film in the Best Adaptive Screenplay, I believe. And this movie is a little bit dramatizing too much about his life. If you watch this film, you might feel Alan Turing was a very miserable person later in his career. It's not. He was actually a very joyful, socially successful person in real life. But you can still learn a lot about his contribution. The reason why I brought up this, his name at the beginning is because he also proposed the very interesting idea, the Turing test. This is considered to be one of the very well-known tests that you can conduct to see if the machine intelligence has reached the same level of the human intelligence. That's a really classic idea. That basically you have the human observer, C, and then this person is interacting with two entities. One is the machine, A, another is a real human, B, and you are only communicating with each of them through written documents. Nowadays, it can be a text. Like you are talking to the real person or you are talking to a chatbot. Based on those text-based information, can you distinguish human from machines? And his argument was that if the rate of mistake you make for each of them, A and B, become the same, then that is a moment when the the machines are as intelligent as humans. So this is what he proposed at Turing test. And quite honestly, in some of the application domains in the machine learning AI today, AI has already passed this test, such as the language models. You see the very sophisticated essays written by machines. Sometimes you see the very sophisticated artwork generated by machines, and you don't really distinguish between which one came from machine AI, which one came from real humans. So in some sense, this test has been broken in many application domains, but this is the historical origin. So another foundational work in this AI machine learning history is the neural networks models. And then surprisingly, neural networks are almost as, 80 years old. 80? Yes. 80 years old, and we are still using essentially the same kind of model. This is the R.M.K, the neuroscientist, psychiatrist, and this is the Walter Pitts, the mathematical genius. He didn't even have any formal degree, as far as I know, but those two worked together to create the first mathematical models of how a biological neuron would behave, mathematically speaking. So this is the first formal model of the neuron, receiving the multiple inputs. Inputs can be a continuous value or discrete value, and based on some weighted sum of those inputs, and applying some nonlinear function like this, depending on the result, this particular neuron is going to fire or remain calm. That is a basic logic gate they created. And they argue that if you have many, many such logical gates, just like in our brain, each one of you have about 1 trillion neurons. Each neuron is connected to about 10,000 other neurons. It's a massive, very complicated networks of this kind of device. They argue that the intelligence would be possible. And it was back in 1943. So AI machine learning has a very long history. It's not a new thing. As you may know, many of the more recent network models are based on this McCulloch-Pitts neural network models. And of course, there has been many revision and modification applied so far, but key idea is still the same. Many inputs coming to each of the device. The device will apply some kind of nonlinear function. Based on that, output value will be 0 and 1, somewhere in between. And then you create massive connections of those. And then especially this kind of structure called a multi-layer perceptron. You connect this kind of module to a layered structure, and the information flows from left to right. This has become one of the most dominant settings of creating artificial neural networks. And then now it's getting better and better in terms of the complexity of such layers. Now it's called deep learning. Deep learning has been very popular buzzwords in AI and machine learning over the last several years. But still, it's really just simulating this for a much, much larger scale. All right? And I would like to emphasize one particular research field, just a historical context. I keep telling AI and machine learning is not new. This is one other evidence. There is a research field called Cybernetics. This is a highly transdisciplinary group of people, as the Dean Chandrasekaran emphasized. Back in the 40s, 50s, 60s, 70s, last century, there were many people, including Claude Shannon in information theory, John von Neumann in computer science physics, and many other people like Heinz von Forester for system dynamics, and you name it, Margaret Mead for system dynamics as well, Warren McCulloch, Walter Pitts. Many influential, very innovative thinkers came together to create a system-based approach. And they considered how to build machines that work with humans, act like humans. And this has been one biggest historical root of artificial intelligence, even though back then it was not called as artificial intelligence. And this name is no longer popular, but we still hear cyber everywhere, like cyber security, Cyber Monday. Cyber Monday is a big online shopping day starting next Monday in the United States, and the cyber world, right? So where does that word cyber came from? Now people use the word cyber almost synonymous to computer, online, electronic. This is the origin, right? So this field created the word cyber that start meaning anything related to computers. So essentially, this is AI. And this is a person who is very well known in the field of cybernetics, Nobel winner. He even published a book titled Cybernetics to introduce the concept, how machine can be intelligent, how machine can also get synergized with other human beings. And this was very popular science book back in the 60s and 70s. At least in the United States, every household had a copy of this book, even though many people did not understand what this means. So this is one first wave of artificial intelligence machine learning. And here I show that the search volume, or sorry, not the search volume, but the number of phrases used in the books and other literature. This is generated by Google Ngram visualizer. The word cybernetics became very popular in the 60s and 70s, and it came down. It's coming back, actually. And the next big wave is artificial intelligence. So artificial intelligence became very popular in the 80s, and it came down in the 90s, surprisingly. So this is another thing I want to emphasize. AI machine learning was not really a new thing. People start talking about it quite drastically in the 80s as the aftermath of the cybernetics move, and then it came down. Now it's coming back, and together with machine learning. So this is something you should know. Any research field, technologies, development, there's up and downs. You should be prepared for this. And people started talking about the machine learning AI. It's kind of in the saturation mode now. Some people start suggesting there's another downtime coming in because everybody now uses it. What's next? Especially if you are studying computer science, data science, AI, you should consider what additional skills you can learn and develop in addition to AI and machine learning. So this is actually a very important thing to consider. Anyway, some other very old-fashioned AI, before the current move of the connectionism, which is heavily based on the connected neural networks, there were also very well-established AI technologies, such as expert systems, logic-based AI, sometimes it's called good old-fashioned AI, GOFI AI, like a GOFI. So this used to be a major approach in computer science, how to create intelligence, based on symbolic knowledge. One still very popular techniques in this field is called fuzzy logic, created by Lotfi Zadeh and many other influential researchers. You could fuzzify, yes, no, true, false based logic to the continuous ambiguity. And this has been still heavily used in industry as well. Okay. And as I mentioned, AI winters here and there. There are many reasons, and the people start to say this might be coming up in the next decade or so. So please be prepared, right? And my hope is that in my lectures, I would like to highlight some of the additional skill set in addition to AI and machine learning so that you can be prepared for all the turbulences coming in this field. Okay, so far so good? All right? So let's start talking about some of the basics, because you may find many of the concepts in the key ingredients parts. Already something you already know. So one is statistics and data analytics. Statistics is essentially finding patterns in the data. You get the data from some experiment observations, and then you plot it. You can also try to fit the mathematical models so that you can summarize how the data distribution looked like. So this is essentially what most of the data science does. Discover patterns. Sometimes I even say, discovering a pattern is like squinting your eyes like this. You plot the scatter plot, you squint your eyes, and then, I see a positive trend, negative trend. There is a trend change at this point. So a much more sophisticated way of squinting eyes could be just a big neural network. You are trying to summarize the data distribution. And one very popular way of such pattern recognition is the regression. Okay. So this could be as simple as a linear regression, drawing straight lines. Or maybe nonlinear regression. You can apply some polynomials but essentially you are adjusting coefficients of those given models so that the data, the provided data can be summarized best by using the specific parameter settings. And surprisingly, this is still pretty much the majority of AI and machine learning does. The model can be different from just a polynomial or linear lines. The model can be advanced neural networks. But still, your main task is to adjust the parameters so that errors can be minimized. And other example of statistics, which is very important, especially for decision making, is hypothesis testing. So this is the group of tools that you can use to come up with some kind of statement by looking at the data. Maybe there are differences between two groups, and you can set the null hypothesis. Null hypothesis is basically the opposite of what you are trying to say. So, such as there are no differences between two groups, and you can choose any of the meaningful statistical testing methodologies to say, what is the likelihood for me to make mistakes if I say there are differences? If the probability of making mistakes is reasonably low, then you say, okay, I will make a statement. Group A and Group B are different. So this has been the very well-established traditional statistical tools to discover some scientifically meaningful statement, such as a typically medical area. This medicine works or not. That's a yes-no answer. Sometimes there are many controversies in that kind of statistical inference approaches, but essentially this is one additional component that can be used in machine learning. And some of you have already learned this probably, right? Other words you might hear in statistical area is Bayesian. Have you heard about this word Bayesian? Bayesian inference. This is yet another school of thoughts, I would say. In the traditional statistics, the concept of probability is always considered to be the frequency. If you have 50% probability, what does it mean? Well, if you try observing that variable 100 times, you should expect to see one option at 50 times, another option at another 50 times. That's a frequency. But there is another way to consider probability. People studying in the Bayesian statistics, they consider probability as how much confidence you have. It's your belief, right? I strongly believe this will happen, therefore I consider probability to be 90%. It's not about the frequency, it's your confidence. So Bayesian statistics chooses a really different interpretation, and in that case, probability will change as you get more observation. This is more related to how you learn the outside world. Initially, you have no idea, but as you interact with outside world, you get more and more data, and your internal belief or representation of the outside world can also gradually change. So that's called a Bayesian learning. This has been heavily used also in machine learning, but still it's just a well-established another set of statistics. Okay? So I hope you will see these words in the future studies. And then now you know, Bayesian, that's just another statistics using different interpretation of probabilities. Okay? So that's statistics. The next historical roots of AI machine learning is optimization. If you have taken any optimization or operations research classes, you will see things like this. The least squares method, one of the most historically established optimization. If you have a data points like this, those red dots, and you want to summarize the pattern by using some kind of polynomials, you can assign coefficient. Equation can be y equals beta naught plus beta 1x plus beta 2 x squared, blah, blah, blah. How do you find the right value of beta? Well, luckily, mathematically, there is a formula that you can use to get the right best optimal beta values without exploring much. So this is called the least square method. Basically, you just need to come up with a mathematical solution that minimizes the errors. Errors mean the distance between blue curves and each of those red dots. So this has been studied for almost 200 years. It's a very well established mathematical field. And more recently, although recent means that 150 years old, there has been also the computational approaches, like this animation. This is taken from Wikipedia. Even if you don't have the exact solution for the optimal value of parameters, there are computational ways to search in the parameter space, and then you can eventually discover the best place that minimizes errors. So this is called the gradient method. Like this. This surface could be a visualization of errors as a function of parameter values beta 1, beta 2. And imagine there is no well-defined formula, but if you know which direction would give you this smaller errors, you can still flow in the parameter space, and eventually, just like water flowing from the mountain to the ocean, eventually you're going to ended up being the minimal error parameter settings. It's very clear, right? So this is called the gradient method to minimize the errors or any kind of function. And surprisingly, this is still 150 years later, what we do in AI and machine learning. We have a gigantic neural network, billions of trillions of parameters, but what you want to do is minimize error. Minimizing the output of those massive neural networks together with what is considered to be the true answer, and you always want to minimize the error between prediction and reality. Still, people are using this, and there has been so many hundreds of improvements of detailed algorithms, but the concept is always the same, right? Some other optimization techniques you may hear, so I'm going to just sprinkle some other relevant terminologies so that you can recognize it. There has been hundreds of years of history of linear programming, nonlinear programming, integer programming, dynamic programming, etc. This is a set of optimization algorithms discussed in operations research. And one thing I want to clarify here is that the word programming in these names are different from programming in computer science. And this is one big confusion. If you measure in computer science, data science, you might consider programming is like coding, right? These names came up at a time when there were no computers. So back in the 1930s, when people say linear programming, the word programming meant planning. So it's a linear planning or nonlinear planning, integer-based planning, etc. Planning in this case is choosing the right parameter values, again. So there are many different ways to come up with the best choices of parameter values. I'm not going into details, but you should know. Some of the literature mentions these names, and you know it. It's just optimization, okay? And other optimization techniques, my favorite, some other researchers start using biological principles, like a biological evolution. Evolutionary approaches, including genetic algorithms, genetic programming, differential evolution, and neuroevolution even. So these are the relatively recent approaches to find the optimal settings using the very biologically inspired heuristics. And this can be combined together with the currently dominant neural network type of approaches. It's actually coming up. The neuroevolution proposed by Stanley Mikulainen, so they are the proponents of introducing biological principles to evolve artificial neural networks. So this is getting more and more popular nowadays. And the inspiration from biology continues. There are many other bio-inspired methodologies you might hear, such as ant colony optimization, mimicking the behavior of ants foraging the food, and the particle swarm optimization, inspired by the behavior of birds and the fish working together. So these are the many other optimization tools. Okay. And terminologies are always confusing, but as long as you know, okay, that's just yet another optimization tool, you feel comfortable. It can be replaced by any other methodologies, right? So those two are basic ingredients, statistics and optimization. They have very long history. Let's now talk about machine learning. So machine learning is really combining those two and together with some other neural networks methodologies to come up with a really sophisticated way to do regression, for example. Yeah, really, finding regression classifiers, that's what machine learning does nowadays. There are several different categories of machine learning, so you may want to know the differences. So I put here 3 different categories. One is unsupervised learning. This is like you just reading a book yourself, alone. Reading a book is a great way to learn, even though there are no teachers standing next to you. So you'll read and you digest, you start forming some kind of pattern directly from data. So finding the organization in the data set. So this is called unsupervised learning. In a machine learning example, this is a group of algorithms that does not require any teacher. Instead, it simply receives data and find patterns. Another much more popular category of machine learning is called supervised learning. This is the situation like you are reading a book aloud in front of a teacher, and as soon as you mispronounce something, the teacher is going to slap your hand. You did wrong. Do it again. Yes, ma'am. And then you go back and you try it differently. So many of the machine learning algorithms, especially used in industry, has the teacher signal. They want to produce a mathematical model that predicts the future, for example, or classify some information. In that case, the user already have the right answer in the data set. And that right answers are used as a teacher. And then if the output of the machine learning is different from the correct answer, you slap the machine's hands and the machine will get a punishment, right? So this is a supervised learning used for regression, prediction, classification, etc. And the third category is for the reinforcement learning. This can be combined together with the previous two, but this is the one particular category of AI, which is for robots, agents, and any other machine that is operating in the real world, such as robots, like a room cleaning robots, Bumper, so they move around to learn about the outside world. So in that case, there is no teacher, but the world itself is a teacher. So there are many algorithms that receives inputs from the actual environment and then try to adjust their behavioral rules so that they can perform better. So this is called reinforcement learning. Okay? Just quickly, so what kind of topics are discussed in each category? Unsupervised learning, there are so many algorithms, such as clustering. You may have heard about any of this. K-means, agglomerative clustering, DB scan, Gaussian mixture, community detection, blah, blah, blah. They're all just algorithms to receive data and find patterns. In this case, it's clusters. Okay. Don't worry too much about the details. People might start discussing which is better, which is worse. Yeah, but those are all problem specific. You just need to know. There are many different clustering algorithms. And this can be useful for anomaly detection, such as you want to find out an individual whose behavior looks weird in the video footage, for example. In that case, you want to cluster human behavior and which individual's behavior stands out. It doesn't belong to any of the clusters. So this can be used to detect anomalies. Again, this is one of the examples of unsupervised learning. It doesn't require any correct answer. Data itself shows the result. Other examples could be feature extraction selection and dimension reduction. Dimension reduction is particularly important if you want to visualize the distribution of data. The data can be 100-dimensional vectors, but by using the clustering or feature selection, you can reduce the meaningful dimension from 100 to maybe 2 or 3. And that can be very helpful for humans to understand the structure of data distributions. The second category, the supervised learning, this one has even more algorithms. such as linear regression, lasso, polynomial regression, nearest neighbor, decision tree, random forest. I just keep talking about this. This just confuses many students and professionals. But they are all just finding regression models, functions that map the input to the output. Some are linear, some are nonlinear, some are parametric, some are non-parametric, but you can use any of them until it works. And of course, it's better to know how they work, but nowadays, each of the functions are implemented as pre-capsulated package functions, so you can use any of them. And very similar tasks are classifications. This is also just a regression, but if the output value is a label instead of a number, it's historically called a classification. You can detect the gender of the person just by looking at their names. Name is a text, output is male, female. In that case, it's called a classification. It's really a regression applied to the categorical variables. And the final category I'm going to just move through, reinforcement learning. They also have many methods such as Monte Carlo method or TD learning, Q learning. So these are all the algorithms already developed to implement machines that can learn through continuous interaction with the environment. Okay? So these are the kind of machine learning. They may or may not use artificial neural networks. But now, many data science areas, people start moving into artificial neural networks. So I'm going to spend some more time talking about this. Okay. So there have been many historically important artificial neural network models. I would like to highlight a few important papers. This is John Hopfield. He was a physicist, and he proposed this Hopfield network back in 1982. This is very different from what we use nowadays, but what he proposed was to create a network of neurons, fully connected. Each neuron is connected to each other completely in the bidirectional connections, and he proposed a mathematical formula to adjust those connection weights so that this entire network can recover the complete pattern from the incomplete initial condition. So this is the example. This is a visual image made of 50 by 50 pixels. So therefore, the number of neurons, each neuron represents one particular pixel. The total number is 50 by 50 equals 2,500 neurons, all fully connected. And if you start this network with this initial condition, spontaneously, this neuron will recover this kind of pattern over time, because this is probably the closest pattern to the initial condition. So this paper was a groundbreaking paper. Memories can be in the interrelatedness of neurons, rather than traditional computer architecture that has a memory space, you assign value to the particular location, right? So if you write something in Python, you could write lists, dictionaries, and in order to retrieve some information, you need to know the key, or maybe the ID, index of the entry you are looking at. That's all the memory, address-based memory access. So he illustrated that the memories can be implemented in a very different way in machines. And that's exactly what we do in our brain, right? We don't really have access to the particular memorization by looking at a certain area because we don't know the address. But we recall something by listening to something imperfect or seeing something imperfect. Our brains will automatically recover the memorized pattern. So that is a historical basic. And this became learnable by Jeffrey Hinton. His face and name is going to show up in the next bunch of slides. You should know his name, especially if you study data science, machine learning, AI. So he is often attributed to be the most influential person who created the current boom of AI and machine learning. He created the revised version called the Boltzmann machines. So this is very much related to the previous Hopfield network. But just 1 year later, they proposed a revised version. This network can learn through repetitive weight adjustment. The previous model, Hopfield network, was not able to learn from the iteration. But the updated version was used in the influential paper 2006, almost 15 years ago. This is the beginning of the current modern AI machine learning boom. So it is the beginning of deep learning, right? And I'm going to show you 3 other important concepts, 1, 2, and 3. Let me go back. Feed-forward neural networks and back propagation. This is proposed by these people, Romeo Hart, Hinton, and Williams, 1986. This is a basic learning algorithm. If you lay out networks this way and limit the propagation of information only to the forward direction, then you can come up with a very mathematically rigorous way to adjust the connection weights by comparing the outputs and the true answer. The errors, differences can be propagated backward. There is a mathematical theories behind it. So this is called back propagation. The original answer was actually, the result was proposed by even another person, Paul Werbers, back in 1974. But this paper in 1986 is often attributed to be the paper that popularized this idea. Okay. The same 3 people published another paper. This is called autoencoders. It's a neural network like this. And one particular task this autoencoder does is that this receives the input, and instead of creating any other value, this network tries to replicate what was given in the input. So what is the purpose of this? If you already have an input, why do you need to care about using neural networks to copy the same information? The value is in the middle. In this network, the number of variables are getting smaller and smaller and smaller. And then in the second half, it's going bigger and bigger and bigger. If you can create the same input to the output by using this kind of bottlenecked shape, whatever is represented in the middle must be the really important information to be able to reconstruct the input. So this can be used for dimension reduction and also information extraction. So one very easy example is how you learn how to write a script, like a letter. Letter A. You know how to write letter A, right? Do you remember every pixel? No, you don't. You see the pixel many times, but after many times of learning, you simplify that data so that one segment going this way, another segment here, there's yet another one in the middle. So the memorization we have about each of letter is very abstract and low dimensional. So we do that all the time, and yet, by using that intermediate representation, everybody can write the same letter A. So that's exactly what this autoencoder does. Many of the AI technologies these days use this basic idea, proposed by the same people, same year. Yet another contribution, again, the same triplets. Romeo Hart, Hinton, Williams published another paper, again, in the same year, to propose a recurrent network. So this is no longer feed forward. Instead, information can go backward. And they propose this framework so that neural networks can learn signals that change over time. And this is very important because many machines should recognize human text or audio, or maybe pictures that if you consider time as a space, the same thing. This allows you to learn long-range correlation in the signal. And the challenge was that, yes, it was okay, theoretically, but at the time, when they published this paper, 1986, it was practically impossible because there are some mathematical issues. How to make this work? It's very unstable. Even if you know the difference between the answer and the correct answer and the predictive work, how to adjust each of the link weights, especially if you have this kind of recurrent connection backward, it would be very difficult to tell, which way you should adjust the link weights. And that's part of the reason why there was another AI winter after the 86. There has been about a decade of silence, okay? And then solution came in from a different group of people. Hochreiter and Schmidt-Huber, 1997. This is a game changer, and this paper is now considered the most cited neural network paper of the 20th century, based on citations. What they proposed was this is the name of the neural network, which is very confusing in my opinion. Long short-term memory, or LSTM. Very confusing. You will see this word somewhere in the neural network paper. This is just the name of the neural network. In my opinion, you should rename it. It's a revised recurrent neural network. So what they proposed was, in this kind of architecture, instead of using simple neurons in each neuron part, let's replace each neuron by more advanced group of neurons. So this is the module they proposed. And this unit will be inserted everywhere in where each neuron used to exist. So by having a more internal structure, they showed that the learning long distance, long-term correlation became mathematically possible. And there is a practical, tangible example that was mentioned by some of the people here. Alexa, or Siri, or Google Echo, you can talk to them, right? Now it became the practically useful tool because of this LSTM. The recurrent neural networks using LSTM can effectively learn very long distance correlation in the audio signal that significantly improved the voice recognition tasks. That's one of the many, many applications. And then now you know the rest of the history. In this century, we use computers to do lots of voice recognition, facial recognition. Many of them actually use this LSTM. Again, it's just revised recurrent neural networks. Okay. There are many other neural network variations. I'm going to skip most of them. Reservoir computing, self-organizing map, neural gas, blah, blah, blah. So there are not just one architecture. People are still exploring many other possible ways of creating neurons. Sounds good? Okay. So I'm going to mention briefly the deep learning in 5 minutes, and then I'm going to talk about the limitations. Okay. Deep learning is really nothing different. It's just a deep in terms of number of layers and the size. So now you can create and train a much, much deeper layer of neural networks thanks to maybe some of your students attending here. Raise your hand if you are the heavy video game player. Okay, yeah, a few people. You must have a really good graphics card, right? Yeah. Thanks to your contribution, this became possible. The GPUs, graphical processing units, that became a huge industry in this century, starting like 2000 later. Many heavy video game players invested thousands of dollars to buy really good parallel supercomputers that essentially worked as a personally available supercomputer to researchers. So they started using GPU's computational power to train this kind of the large-scale neural network. It was not possible before the GPU. And also, the widespread internet allowed people to share really high-quality standardized training data set. So that also accelerated the research of deep learning. Some of the applications, the convolutional neural network, CNN. This is one common example of deep neural network in which mathematical operation called convolutions. That's really just applying some kind of kernel function around each point. So this turns out to be a very effective way to recognize image, for example. This is Jan LeCun, very famous AI researcher based on New York University. One example like this. After training this convolutional neural networks, you can show the bitmap image, and then after many layers of convolution, you will get a numerical vector representing which picture this is most likely. You have the highest value for car, a little bit less truck, and air, maybe airplanes, etc. So this is one example to detect images and extract the concept. Yet another very popular and cool topic is called GAN, Generative Adversarial Networks. This is proposed by Ian Goodfellow and his colleagues. The basic idea is that instead of designing just one machine, one neural network, you should train two of them and let them fight against each other. So that was the basic idea. That's why it's called adversarial. What he demonstrated was this. These are the pictures. They look very much real pictures, right? Real human faces, but they are fake. They are coming from the generator of the face generation neural networks. So one neural network in this case produces human-looking face image. And its competitor is a discriminator. It receives the output of the first neural network and then tries to tell, this is a fake, this is a real. So you evolve both of them simultaneously, and then they get better and better and better to outcompete your opponent. So through this process, both of them get really, really good. So this is how they, the Ian Goodfellow, created almost human indistinguishable quality of the human face images. So this approach can be used in many other applications. The key idea is create two machines and let them fight. Although the idea itself has been around for many years in the AI community. I'm going to skip this slide because this is not so much relevant to many of you, but there is also yet another version of neural networks applied to study the data set that are like the social networks. So it's called a graph neural network. It's also coming. And finally, the word transformers, you might hear this in some of the literatures. The word transformers mean many different things in engineering. If you measure electrical engineering, transformers really mean the actual device that changes the voltage of the AC current, right? In the pop culture, transformers can mean a robot that transforms from the truck to the humanoid robots in the American comic. But in the machine learning area, the transformer means a language model. Very confusing name, I know. So this is proposed by many people, and there's a very famous paper by Vaswamy et al. In 2017. It's very recent. The title is very sensational. Attention is all you need. That's a very famous paper. Basically, they propose to decompose the human sentences, languages, into localized structure. They basically ignored any possible long-range correlation in human-generated sentences, just focus on the attention structure in the local region in the sentence. So that strong assumption made it possible to do the massive parallel learning. If you have the 10,000 words of text, forget about correlation between the first word and last word, and just learn any piecewise way. That parallelization made the training of the large-scale language models possible. And one tangible example is called BERT. This is the one example of transformers created by Google. So that was a time when Google search became very good at typing and making a prediction. You type some keywords, suddenly Google starts showing there's some possible following words. That is coming from BERT. And later on, there are more and more competitions going on. OpenAI, this is created by Elon Musk. They proposed a very impressive language model called GPT-3 2 years ago, and some others. Google also does the same thing. And the rumor says that there is another version, GPT-4, coming up soon. How many? They are basically just gigantic neural networks. How many parameters are included? Well, GPT-3 uses several billions of parameters, billions. It is rumored that GPT-4 will contain 100 trillion parameters, trillion. That's a massive AI model. And compared to how much information your brain has, I said each brain has about 1 trillion neurons. Each trillion could be connected to 10,000 other neurons. The total number of parameters, if you consider this as a neural network, is 10,000 times 1 trillion. It's a 10 quadrillion parameters. That's the number of parameters each one of us has. Now, machine is approaching 100 trillion. Maybe a few more order of magnitude, the machine's degree of freedom will be competing with our brains of actual natural degree of freedom. That is coming. I'm sure that moment will come in your lifetime. It doesn't mean, in my opinion, singularity. It's really just a massively complex language model, which might be very useful for students to write an essay, for example, or for faculty to write an annual report. But what does it mean? Well, you will see in the future. Okay, and as some of you already know, most of those deep learning and artificial neural network methods has created a lot of social success. You know, some amazing essays written by machines, amazing artwork generated by machines, and there are many publicly available algorithms like a DALL-E, DALL-E 2, and nowadays Mid-Journey, Stable Diffusion 2. Those are just the names of publicly available art generation engines. So people get really fascinated about most of those technologies. Okay. And I'm going to skip some of the topics because we are running out of time. Things that we didn't have time to talk about include time series analysis, NLP, natural language processing, and information theory, computation theory. They are all very important components of machine learning you may want to study. And a more deep connection to other disciplines. AI and machine learning can be very informative as a model of human brain. So brain neuroscience has a lot to say to AI and machine learning. Complex systems, networks, that's obviously my research area, and robotics. And finally, if we want to understand scientifically what is a consciousness, why we are so intelligent, why do you have a self, yourself, somewhere in your brain? Those are really the fundamental philosophical questions. AI and machine learning could also make huge contribution, but I didn't have time to talk about this. Okay. And if you want to move into this area, there are many tools available. By far, the most popular language choice is Python, obviously, and there are several packages, such as scikit-learn. This is the comprehensive statistics, the machine learning framework. You can do a lot of stuff just by using it. If you want to do more advanced deep learning, artificial neural networks, you can use TensorFlow Keras. This is supported by Google, or maybe PyTorch. This is maintained by Meta, Facebook. Now, there are several other tools available. Okay, so I'm going to skip my own research examples because these are just examples of how we can use machine learning AI in the actual research. I'm going to skip these. Let me summarize this. Should we have a break? Give me 3 minutes. Challenges. Even after so many successes in the AI, we still have lots of issues. For example, these are the images created by AI. One example, the sentences generated is completely gibberish. There's no meaning here. Second example is the concept of numbers. The instruction said, give me the picture of 7 people. And the machine had no idea what 7 means. This is very ironic because computers used to be good at handling numbers, symbolic computation, and yet in today's neural network-based AI, computers are really terrible at words, numbers, and scientific facts. This is the picture machine generated when it was told to create a picture of a solar system. How many planets are here? Well, we are supposed to have only 8 planets, but machine have no idea what it is. Okay. Machine can also forget everything catastrophically if you keep teaching lots of stuff. This is never the case for human brains. We can continuously learn new stuff, gradually forgetting what is not so important. But that capability is very difficult to achieve for machines. You teach million things, and at some point, machine forgets everything. Right? And finally, the transfer learning. It's extremely difficult for machine to learn one thing and try to generalize the knowledge to another task, even though humans are very good at doing this. Like learning how to play a musical instrument, you become good at learning another instrument. Machine cannot do that. Other more technological concerns. Now, because AI is getting too big and resource demanding, there's fewer players who want to hoard all the capability, like Google, Facebook, Amazon. They offer AI technologies on the subscription basis without releasing all the details. So this kind of over-concentration into a fewer number of players must be very concerning. Another issue is explainability. Neural networks, many other AI technologies are black box, meaning that you get output, but you may not know why and how the AI makes those decisions. And this is very concerning if you are a decision maker, right? If you are CEO and you are trying to make a hard decision, can you outsource everything to AI? Well, many people would not be comfortable doing so. So therefore, there has been the huge demand to convert AI machine learning to be more transparent so that the mechanisms AI uses should be understandable to humans. Another very important challenge is a bias. This is a very famous, almost internet meme. Do you guys know who this is? Pick a person pictured on the top here. His name is Mitch McConnell. He's a politician in the United States, Republican. And who is the second person here? This is everybody knows, Obama, right? So there was a person who created this kind of image. At the top, you put the Mitch McConnell's face. At the bottom, you put the Obama's face. The Twitter automatically focused to the white person based on the facial feature, even though, politically, socially, Obama is more important, in my opinion. And he tested swapping the order, and yet Twitter always focuses on the white person because the training data was predominantly white. So this is a very important issue. Machine learning picks up any kind of biases included in the data. If we want to do some socially useful AI, we really need to have a good representation. Other issues, obviously, fakeness. These days, you never know. The movies, video clips, or images circulating in the social media, are they really the true videos? Or maybe it's just a fake. So it's getting really, really close to the real footage. So it's very difficult to tell the real thing versus the fake. And also, this also gives us a lot of challenge to the professors in the university. Students have access to language models. Chances are they are using some automated essay writing AI. It's a huge challenge. We need to come up with a solution for this. Okay? A few more challenges. The energy consumption. This is really, really critical. Training trillion parameter learning models, it takes a lot of electricity. A lot. So this is the histogram showing the amount of carbon dioxide produced by one person traveling from New York to San Francisco across the entire continent. This is the amount. This is the amount of the one language transformer. One training alone produces this much of carbon dioxide. Is it really worth it? So by having a massive advanced AI, we might be destroying our planet. It's a very concerning issue. And finally, this is actually very important for people who are studying data science. There are many situations where people need to make a decision even without the data. And this gives you a lot of conceptual challenges. AI machine learning needs data. But there are people who need to make a decision without data, such as the beginning of COVID-19. 2 years ago, nobody knew what was going on. And that many university administrators, public health administrators, they need to make a hard decision. What else can we do as an expert who has computational skills and data science skills, even if there isn't much data? That's another very important challenge you may want to consider. Okay? Rights of AI, this might be coming. AI might be considered to live alive. If so, do we have enough legal system? How to protect their rights? I'm sure in your lifetime, there will be some serious lawsuits coming up because someone killed AI. And this is the last challenge I would like to emphasize. All of the AIs that I discussed here, simply put, they are just mimicking people. Something was done by someone else, and the AI learned from the people's past work. In that sense, is there any creativity in the AI? For example, can we have a person like a Picasso? Picasso generated Cubism as a new drawing style. Nobody else tried that kind of very weird but very innovative drawing style. So what he did was he didn't use any data, but instead he came up with a completely new style by exploring the artistic, the drawing skills. At least in today's AI, no machines could create something new as Cubism, but humans can do. How can we achieve that? It's called open-endedness. Is it possible to create a creative engine, machines, neural networks that keeps producing something as novel as Cubism, right? After all, are we really getting closer to any intelligence? And this is something that I don't even have an answer, so you may want to continue asking. Are these entities, machine learning, algorithm, etc., are we getting closer to the true intelligence as we consider we have? It's called a general intelligence. Can we do that? Nobody knows. Even though the current AI models can be very fascinating, many people say we are not getting any closer to the true intelligence at all. So that remains a huge scientific and philosophical challenge. Anyway, so that's it. Final remarks. Don't worry too much about those confusing words. Be focused on what you want to do. And use any kind of tools of your choice. It can be statistics, it can be neural networks. They are available. Use it, but don't forget about your task. Right? The problems you want to solve, tools are available. They are just tools. So I would like to thank many people who contribute to this, and I'd be happy to take any question. Let's have a short break. Thank you.
Thank you for the informative session, sir. I request all the participants to have a break. You will be provided with refreshment and be back after 15 minutes sharp at 11:30 for the next session. Thank you.
Thank you very much.
Participants, if you have any question, you can ask. You can ask after the session, after the break. Participants, you can settle down. It's 11:30, we can start the session. Participants, settle down fast. You can start the session. Participants, if you have any question, you can ask the guest. Any questions? Participants, please ask your questions.
Any question is fine.
Sir, these AI techniques can be used in washing machines and refrigerators.
Sorry, could you repeat your question?
Sir, these AI techniques can be used in our washing machines. Daily we are using in our houses. Suppose if the machine says only 10 kg of dresses means how we are not calculating and we are not weighing and putting in the machine. But anyway, the machine is accepting that.
Yeah. So you are talking about the specific application domain of AI. Yeah. So I'm not sure if I fully understood which particular domain you are talking about. Yeah.
We have washing machine.
Washing machine. Okay.
Washing machine.
Yes.
He says that, today I may load the washing machine with 10 kgs of material.
Yeah.
Next time I will load only 5 kg.
Yeah.
Whether the machine will take care of that, to supply.
Yes. Yes. Thank you very much. Well, that has been the really traditional appliance industry where many AI technology has been already used. So it's there already.
Washing machine.
So for example, I came originally from Japan. Japan has been using the neural fuzzy application in the washing machine, refrigerators, you name it. There are many sensors and the decision makers already implemented the appliances. And now it's getting moved into like a cooking. So this is happening also in the United States. The advanced AI-based cooking, you just download the recipe and you put the ingredients. The system is going to automatically measure the weight and then adjust the time. So that is already done. Yes, absolutely. The answer is yes.
Any other questions?
Good morning, sir.
Good morning.
My question is is the AI system is implemented in DNA separations or any other biological fields? I have to know about that, sir. Can you explain?
So the application to biology, you asked?
Yes, sir. By separating the DNA strands using
DNA.
Yeah.
Okay. Yeah. So AI and machine learning has been heavily used in system biology already. So because after all, it's a computational task, and one important application is the drug discovery, right?
Okay.
So you need to find the drugs that actually works. For example, COVID-19 is one example. What kind of the protein sequence, the gene sequence would be helpful? And then many AI application has been done to search the possibility space. So it's heavily applied already. Yes.
Thank you.
Sir, myself, Dr. S. J. from Tech. Sir, what is a specific application of AI in medical field, sir? especially in drug delivery?
Yeah, many applications in medical field. That's actually one of the most widely explored fields, including diagnosis. Obviously, there are many medical data to which you need to train the machine learning algorithm to diagnose what is the disease, or is this cancerous or benign? That's a really typical thing, like X-ray pictures. And usually radiologists and medical doctors look at each of the pictures, but there has been a huge need to see if this image has a higher potential to have cancer. That's only one of the many examples. Other areas are, just like I mentioned, the genetics. So if you have genetic data, you can extract lots of information from each person's genomes. And also some other tangential issues include healthcare operation, like financial things and whether or not the behaviors of each patient. If you administer some medication to the patients, are they going to follow the instruction given by the physicians? If there's a higher risk, you need to take some intervention so that they make sure they take medications. And then there are lots of machine learning algorithms applied to predict who needs care, who is more autonomous. That are just three very small number of set of applications, but it's hugely active research area. Should we move on to the next lecture, or do we have more time for Q&A? Yes.
So I would like to know that in artificial intelligence, is there any other language we should know other than Python?
Absolutely. Python has been very popular because there are many libraries available, right? But my recommendation here is that everybody is learning Python now. Not just you, but every other cool kids out there, computer science major, even high school students. Some of them are really advanced, so they learn Python. So that means you have to learn Python, but you have to learn something else as well to make a difference. My recommendation is Julia.
Once again, sir?
Sorry?
What are the language?
Julia. Julia is Julia. That is my favorite. Probably you have learned how to use Jupyter Notebook, right?
Yeah. Yes,
sir. Jupyter means Julia, Python, and R. Did you know this? It's designed for 3 languages. R is very popular for data analytics. Python is very popular for machine learning. Julia is very popular in scientific computation, including machine learning as well. The main difference is that Julia is a compiler-based language. It's fast, and it looks like a Python. So if you can code as easy as Python, but you get 100 times faster speed, why not switch to Julia? So that is happening right now. So better to learn it now.
Thank you, sir.
Yeah. Okay. Thank you very much. Oh, one more question. Yes.
Hello, sir. This is Jolish. I'm a PhD scholar. So Q-learning and Monte Carlo are some of the reinforcement learning algorithms. So basically, we don't train the algorithm using data, right? Can you please explain about it, sir?
Yes. You are asking the question about the reinforcement learning, right? Yeah. So in this case, training do happen, but training is not based on data, but instead, agents, machines are already in place in the environment, and the learning takes place through the interaction with the environment. So in other words, that's exactly what we are doing. The human being, you are living in this physical world, unless you are isolating yourself and virtually interacting with the people. So we are embedded outside. Every day, every moment, you have inputs coming from the environment, and you adjust your thinking based on what happens. So that's essentially the data for reinforcement learning.
Okay. We deal with real-time data.
Sorry?
Real-time data.
Yes. So it's the data that happens in the world over time.
Thank you, sir.
Thank you.
Any other questions?
Hi, sir. This is Aditya. And my question is, what do you think about development of machine learning and AI applications in parallel reality, the future technology? Is that possible or not?
You said parallel?
Parallel reality.
Parallel reality?
Yeah. Can we develop?
You mean virtual reality?
Yeah, virtual reality.
Yeah,
the
metaverse.
Future of virtual reality.
Yeah, it's already happening.
It's already happening.
It's already happening. So,
can you explain it briefly? What application is developed?
So Mark Zuckerberg made a big splash that we are going metaverse, but he's so old. It's not like what Meta is creating. The metaverse has been around for many years already. Many virtual reality enthusiasts are already creating universes, like a Minecraft. Minecraft is one example, by the way. And the cluster and the VR chat. In many those virtual realities, people actually can program entities that are based on AI instead of real humans. So you go out in that virtual reality parallel universe, you interact with other people, but you never know. That might be actually the chatbot. It's already happening. So it's like a real Turing test. People can still see this is an automated computer-generated character, but it's getting better and better. And at some point in time, I mean, like 3 years from now, 5 years from now, those virtual reality worlds can be full of bots. Just like what happened in Twitter. Twitter, like, I don't know, 20% of users are actually bots. Same thing is happening in the virtual reality right now.
Thank you, participants, for your valuable questions, which would help the other participants too. It's time for the second session.
Thank you very much.
Please, sir.
Thank you. So in the next hour or so, I would like to give us 2 short presentations to summarize what else you can do. One is a continuation from the first lecture about AI and machine learning, but with the computational power you have, what kind of additional thing you can do just to supplement the pattern discovery capabilities that the traditional machine learning does. And this is going to be about 30 minutes, and then immediately I'm going to switch to talking about the system science as a discipline, so that maybe some of you might be interested in studying this field. So let me begin. So this talk title says Mechanistic Modeling of Complex Social Systems. This is related to my own research area as well. The key thing about this talk is about the word modeling. Many people consider in machine learning AI, modeling is really about the statistical machine learning models. So this has been very dominating way of understanding modeling. We have already discussed in the previous lectures. It can be statistical model, neural networks, convolutional neural networks, or maybe language models. So they are all considered as models. Almost automatic, when you say a model to the people who study AI and machine learning, they automatically consider models mean AI, machine learning type of models. But one thing I want to emphasize, you guys realize, and then maybe stepping back from those currently dominant way, is this. What is a model? There are many different meanings of this word. If you talk to physics people, physicists consider this is the model. This is a standard model of particle physics. It's basically a collection of all the elementary particles, like quarks and leptons, gauge bosons. Don't ask me anything. I have no idea what they are. But this is called the standard model, the model of the physics. Okay? Very different from machine learning. If you talk to biologists, they consider these animals are model organisms, such as the tardigrades, some kind of unicellular organisms. This is a hydra, some kind of amoeba, fruit flies, or even bigger ones like mice and pigs. You use those animals for experiments. They are called models in biology. If you talk to management people, they may say, oh, we are using a PDCA model for our management. This is the procedure they take to make a decision. Plan, do, check, act. That cycle. If you rotate this cycle, your organization should get better over time. That's the model they talk about. Okay? In my research area, complex systems, network science, models usually mean computer simulation models, such as chaos, as Professor Chandrasekhar mentioned earlier today, as well as models, agent-based models. So these are typically the models we play with. But finally, if you go outside of the academia or science, you just randomly talk to the person on the street, and then you tell them, I do modeling, you might get a very wrong impression because people consider modeling like this, a fashion model, right? You come out to the stage with a really nice dress and you walk like this, that's a modeling, right? In all of these cases, the word models means something. It's in common. what is the common among all of these, including the machine learning models? The common idea of the modeling is to represent something in a simpler way. Okay? If you have a description that is simpler than reality, that is considered a model. Machine learning models simplify the structure in the data. The standard model in physics simplifies how universe works, etc. Even the fashion model. Fashion models represent human beauty by using their face and the attire and the style, the behavior. So they represent something else, right? So thinking this way, modeling can mean many different things, not just machine learning. And that's something I really want you to understand. There are two different ways to approach modeling in science. One is something we already covered extensively in machine learning, pattern discovery. And this is where I want to emphasize what is the extra thing you can do. As I mentioned, everybody is learning machine learning AI now. So everybody is really good at recognizing patterns, discovering patterns in the data. The additional component, which is almost equally important, in my opinion, is mechanistic modeling. So I'm going to explain a little bit more about this. If you are good at both of them, your future career will be much more successful than just a typical data science person. Okay. Pattern discovery. This is something we already discussed in the previous lecture. You have a data, and you try to find patterns. You can use statistics, machine learning, data science, AI, classification, etc. This has been done many, many hundreds of years. Mechanistic modeling is also very old, and this is complementary to pattern discovery. So this effort is to come up with the explanation. And this is what somewhat related to one of the challenges I mentioned, explainable AI, right? How to make the discovered pattern explainable to humans. And that is still underdeveloped field in AI because it requires the skills of mechanistic modeling. So what are the models in this case? Well, it could be theories, principles, or equations, simulations, any organized way of representation that explains how and why the data looked like this. Okay, I'm going to show you one example. Oh, by the way, so my point is that science needs both. And all the computational professionals should know both sides instead of having just data discoveries, data exploration, pattern discovery alone. One easy to understand examples. People are fascinated by astronomy, like a planet, solar system, etc. Yeah, thank you very much. That's 1,000-year-old data science in the humanities history, right? People, even in the ancient era, like 4,000 years or 3,000 years ago, people went outside and looked at the sky during the nighttime. They collected data, the location of those bright dots. And then the clustering can be making constellations. These dots look similar to each other, and then you connect the dots, and then you name it. This is the constellation of the Big Bear, for example. That's a clustering. And anomaly detection happened. Some people discovered that certain light dots behave differently from the rest of the patterns. What are they? They are planets, right? Those are the objects that exist much closer to us. Therefore, their behavior is not following the global rotational pattern. And there is actually a very interesting object discovered more than 100 years ago. Have you seen this kind of picture? This is a physical object as big as this much. This is the real thing. It's called Antikythera mechanism, recovered from the shipwreck near Greece at the beginning of the last century. Initially, people had no idea what this mechanism was. It looked really advanced technology with complicated set of gears, and later people discovered this is a mechanism that automates the computation of location of sun and moon and the planet. Basically, you adjust the dial, and then automatically it tells you the location of the solar system's objects. It's an amazing mechanism, and it was almost like an Apple Watch back in the 2,000 years ago in the ancient Greece. But my point here is that this is, well, surely this is a mechanism. It's made of gears and the physical object, but this is not the mechanistic model, as I say. This is simply automating the calculation process by exploiting the periodicity of the location of planets. So there was some genius people who designed this mechanism to get a shortcut in making prediction. However, this is not what our the solar system look like. It's completely different, right? So therefore, in some sense, this is the current machine learning we are using. We have a shortcut of the prediction by using whatever black box mechanism, and yet it doesn't tell you much about the insight into the actual mechanism by which our solar system is operating. The real mechanistic model, I would argue, looked like this. So these are the pictures of the geocentric model of the solar system. There was a time for many hundreds of years, the humanity believed that the Earth was the center of the universe, right? So people put the Earth at the center, and then they created this kind of the orbit. Many objects of the universe rotate around the Earth. It's called the geocentric model. And this is also the real mechanistic version of how the solar system behaves. This is what I mean by mechanistic model. Is that clear, the difference between this Antikythera mechanism, which is mechanistic physically, but it's not a mechanistic model of how the solar system works. This is more like a theory-driven. It actually illustrates how the mechanisms of the solar system is operating. Is that clear? So the main benefit of having this kind of mechanistic model is that you can create even deeper insights. The scientist named Copernicus, he proposed to put the sun instead of Earth in the middle of the solar system. It's called the Copernic Revolution that took place many hundred years ago now. So this allowed other researchers to come up with insights like this. You guys recognize what this is, right? The Isaac Newton's law of gravity. Force determines the movement of objects, and the force created by the gravity is given by this formula, gravitational constant times mass 1, mass 2, divided by the distance squared, etc. This is the beautiful simplification of the governing role of all the mechanisms here. And this would not be possible if people stayed at this automated yet black box computational device. Is that clear? And this is really necessary to do anything further in human history. Because of this, we were able to predict the trajectory of an unknown object or man-made object. Eventually, another several hundred years later, we became capable of sending the space probe to the really far deep universe. Okay. This kind of jump required this, which is facilitated by the mechanistic modeling. So that's my whole point. I hope you understand, right? So my argument here is the current AI, machine learning, is around this stage. People is trying to make a jump from here to there, and that's going to be the additional skill you want to learn to complement your skills in AI and machine learning. So, sorry, something happened. Yeah. The reason why the mechanistic modeling is needed, not just in astronomy, but the social, political, economical, ecological things, is because now the problems are getting more and more complex and uncertain, as the Dr. Chandrasekaran mentioned earlier, VUCA, right? So the things are getting more uncertain, ambiguous, and complex. And also, as I mentioned before, the availability of data might be limited in the global challenges like COVID-19. So in that case, you really need to have a mechanistic model rather than just data-driven approaches. And also, and especially this is true for the last 3 years when everybody was suffering from COVID, prediction turns out to be not so useful after all. People make lots of predictions. Next day, it was proven wrong. And any decision made based on the accurate prediction becomes useless in the matter of days. So in such uncertain situations, the value of prediction is getting really, really small. What is more valuable is preparation. Instead of trying to predict what is going to happen tomorrow, let's consider what are the possible future courses, explore many of them, and then try to understand what we should do in order to be prepared for the many different scenarios. And this is going to be more important ways to use machines. Think about the global climate change. How many degrees of increase we are expecting next 100 years? People argue, yeah, I predict 1.5 degrees. Some people say, no, 1 degree. Some people say 2 degrees. My point here is that it doesn't matter. We need to be prepared for the worst. So that's why mechanistic modeling is really important. So in this talk, short talk, I'm going to mention 2 examples where traditional AI machine learning model is not really easily applicable. One is the COVID response planning. So this is what we did. The Binghamton University campus needed to reopen its campus even during the pandemic. We officially reopened the campus back in the fall semester of 2020, and one of the decision-making processes involved the system modeling ability. So somehow my university president, President Harvey Stinger, he got the phone number of my own mobile phone, this one. He called me in the Saturday morning. I was completely shocked. Before that, I had never had a direct conversation with my university president. He said, Hiroki, can you do this? So he requested us several tasks. One of them is to build a campus traffic pattern simulation, because the university administration needs to know which location, what time, how many close social contact would occur on that campus. So let's use some system modeling so that the university can make a better decision of how much population size reduction would be needed. And this was a really challenging task. Well, in order to simulate human behavior, we need to have the human behavior data. That's how usually the data scientists would think. We didn't, because if the university were tracking every single student's movement, how do you feel? Are you comfortable being tracked? No, never. It's a huge privacy breach. So obviously, we didn't have any direct data set to simulate the human behavior, so we need to create a theory by using any kind of indirect data available. Okay? So this is what we did. We first created the road pattern mapping from the Google Earth. This is a map of the university campus from the top view. There are roads for the vehicles, and there are many smaller pathways for pedestrians. Location for classrooms is pictured here in the pink. Those green dots are the residential halls. Blue circles are parking lots, etc. So this is the underlying structure we used. And we basically contacted any department who could be helpful, because we simply didn't have data. So there was a lot of thinking process, calling people, writing emails. So we are supposed to create a system model of the entire campus. Could you help us? And then we reach out to registrar's office to get the course schedule and locations and students' enrollment records. Who is signing up for which course in the previous year? And of course, all the names are removed for privacy, but we get anonymized data set. And there are many other data collected. And this is not a data science. Now what? You need to think. It's like a forensics. Are you guys familiar with forensics? That's a scientific practice to find out anything related to crimes. Crime happened. Nobody was looking at this scene. But your job is to reconstruct the story. What happened? And you need to talk to a bunch of people, getting indirect evidences. Well, he was there. Well, I saw her walking this way, blah, blah, blah. Many different stories, indirect stories. Nothing is telling the exact behavior of the criminals at the crime scene. But we need to reconstruct that. So lots of thinking, creative process. And we made lots of assumptions. I'm going to skip the details. But I assumed every student's going to go to every class. They will never skip any single class. You agree, right? And they are very diligent. They are not going to any other Friday night activities. They go back home after the class, etc. Then we get this. Let me try playing this. Here's an example of the computational simulation you can construct that goes complementary to traditional data science. So the dots you are seeing is the individual student, faculty members, and staff, every single person who existed on our campus in the fall 2019 semester, they were simulated here. The total number of agents, they are called agents, were more than 17,000. And they move from place to place, and those green desks are going to get bigger if there are more occupants in each building. And the parking space also gets bigger and smaller based on the number of parked cars. Right? There are lots of details simulated here. And as you notice, there's a heat map occasionally appearing. That is the number of close social contact we detected in the simulated system. How many times two agents get closer than 2 meters, or 6 foot in American scale, for more than 10 minutes. And you can actually count every single such contact. Now it's done, right? So this is one example how you can create the dynamic system model even though you don't have enough amount of data. And you guys already have a basic skills to do so. So please realize you have a superpower, right? And this is actually a very useful tool. Oh, sorry. And we also did some calibration by using parking usage data to make sure this is not so crazy. The benefits for the decision makers is that now you have a system model which is not based on the actual data, but based on our understanding. We can create this kind of summary. This is a heat map that aggregates all the possible contacts over time. Just to let you know, this is the location of the lecture hall in our campus. This is the food court. Students go back and forth between lecture hall and the food court to get the food, obviously. And this part is the bus terminal. Many students depart outside campus to go back in home. So this is the big pathway. University administration need to do something to control students' behaviors. And another benefit, how many people are familiar with the Infinity War? Raise your hand if you have watched the Infinity War. Okay, about half of people. For those, you know what this means, right? So having this kind of system model, you can easily snap your fingers to kill 50% of the population, easy. No ethical concerns. So we were able to conduct this kind of counterfactual simulation. This is yet another signature moves of the system modeling, which is different from data science. Data science is about finding patterns in the data. But system modeling allows you to explore other alternative hypotheses that never occurred in reality. So here's a result of the, so this is the simulation with 50% of individuals randomly eliminated, just like what Thanos did in the Infinity War. And you get the results like this. We can go even more than the Infinity War. You can do it twice, right? And then you eliminate another 25%. Now there's only 25% of human beings remaining in the world. Here's the result. Yeah, very different. And this is the total cumulative pattern. Basically, all the social contact is gone. So this is another benefit, and also it relates to the preparation argument I made. You need to have a system model like this in order to conduct a systematic consideration of what could happen if you apply some non-real assumptions. And we conducted this in a very systematic way. This is a summary. The horizontal axis is how much population is kept on campus. Vertical axis is how many close contacts existed per person per day, right? So this would not be available if you are only looking at the data. And after many considerations, we applied some of the analyses, including economic evaluations, epidemiological evaluation. We discussed that maybe this 40% would be optimal. We maintain enough number of students on campus, yet with this density, probably under very conservative estimates, disease will not spread on campus. And the university applied this. And then we moved a certain number of courses to online. The actual presence of the students and faculty are kept below 40%. It was a success. University was operational even without any cluster infection. So this is one example how you can use computational tools that go beyond the machine learning to make hard decisions. There's also the story that goes behind the scene. This was a success because we didn't have any cluster infection on campus. But what we were wrong is the students' behavior outside the classroom. Our assumption was just too naive. Students went outside, students had to hang out and going to the bar, etc. It is difficult for us to control students' behavior beyond the actual simulated time. That's where infection still happened. So we still learned a lot. We still need to learn humans, right? But anyway, that's another story. The second case study. I'm going to skip this maybe because we are running out of time. We need to finish everything in 12:30. But just to illustrate, one more possible case of applying system modeling is to explore the possible society state. We live in the current society, we have only one such examples. But can we explore different forms of society to achieve the better social state? So we have been working really hard to explore the issue of social fragmentation. This happens everywhere. In the US, for example, there are many social conflicts between different sectors. And this is not only about the ideological serious cases. It could also mean that some culture, like the food preferences, especially in the US, the very extreme veganism emerges, as well as very extreme meat-eating habits. So this is fragmenting. And this is yet another cultural thing. So people can actually go extreme to dress like this. This is not even Halloween. So people can dress like this and walk, right? So in all cases, people can get really extreme. Why is it? So we created a mathematical model to simulate the behavior, something like this. Let me try, oh, sorry. We need to run the simulation. This is yet another system modeling, which is not direct application data science. So you just saw the initial social network, which is fully connected, and each node has a color value. That's the culture of the opinion. Over time, when you integrate numerically these equations, you will see that networks are going to spontaneously self-organize into clusters with similarly opinionated people. So this would be another benefit of making something invisible to a visible scale. So we can simulate the hypothetical social evolution process by changing parameter values, what kind of outcomes we're going to get. Okay. Without going into much details, I can just show you the summary. So what we discovered by conducting many different parameter settings, as I said, this is not for prediction. Let me re-emphasize it. This is not a prediction, but we explore all the possible scenarios. So this result summarizes what kind of social state we could get if you change three parameters, H, A, and C. C is changed in different panels. Blue parameter settings mean that the society gets homogenized. Everybody gets connected to each other, and they are basically speaking the same thing all the time. Is that good? No, I don't think so. You lost idea diversity. And the red regions mean the society gets fragmented. The society completely lost the connectivities, and the many clusters are talking their own things. The idea is diverse, but the information flow is lost. Either is not so good, in my opinion. And we can illustrate that the parameter settings, such as this, under the small parameter value C, it's called the social conformity, you have basically a competition between those two parameters. In the high social conformity, we get another phase transition line here, right? If you have the relatively high number of social conformity, it actually helps society to get homogenized. So these are the kind of things you can run by conducting large-scale numerical simulations. It's very much like an engineering study. Okay? And you can learn a lot of stuff from this type of a hypothetical social simulation. There are two mechanisms that are found to be conflicting with each other in this case. Social conformity, let me go back. Social conformity, this means behaviors like this. Tiny boy here, he is behaving like those two other old women, men. It's a behavioral contagion. You become like your social neighbors. This is happening all the time. You learn from your friends, right? The other dynamics is the homophily. You hang out with someone else, like a bird of a feather effect. You get closer to each other because you are already similar, right? Now, my point here is that if you only look at the data science, they are indistinguishable, right? This looks like three people look similar. This looks like several people are similar. Observation-wise, you always see the same consequences. People look similar in the social neighborhood, right? In order to distinguish those two, you need to think about the process, mechanistic models like a gravitational law, and then that gives you the huge mathematical differences. This is about changing the node state. This is about changing the connectivities. So therefore, it's edge dynamics, and then our simulation results show that their outcome is completely different. So this is yet another example how the mechanistic modeling can give you the insight which is not available in typical data science. Okay. I'm going to skip all the implications here, but essentially the social media platforms has a major implications of how the society will evolve by using that kind of particular interface. Okay. And we are also exploring how to create yet another currently unobserved social state. Like, is it possible to create a society where people are different but still talking to each other? So I'm going to skip this part, but we also have the simulation models. Maybe I can, yeah, I'm going to skip it. Oh yeah, here you go. So this is yet another simulation model that tries to find out any unobserved third state of a society. Yeah. The answer is we discovered some conditions. That's another story. If you are interested, please read the paper. We get this kind of states. That's a hypothetical society as it could be. Right? All right, let me conclude in 2 minutes. The summary of this presentation is to provide a complementary skill set that you already have. So mechanistic modeling. In addition to data science and the machine learning, that's actually a very important toolkit you need to learn and be able to use. But what's missing right now in the predominant machine learning area is to create explanation models that actually allows you to simulate counterfactual situations. And that is becoming more and more useful because there are many increasing number of situations where there are no data available, at least at the beginning, and there's a huge uncertainty in which people need to get prepared instead of trying to predict exactly. And the next generation of AI, machine learning, data scientists, I mean you guys, right, need to be able to do both of them. Data analysis, pattern discovery, together with the mechanistic modeling to come up with the narratives. You need to be able to tell the story. That is going to be a very important skill set in the future. So right now, the market looks like this. Pattern discovery is dominated because it's still a good money maker. You can still make a lot of money by just making prediction. And what's left behind is gaining insight. That's your job. You need to make a right balance. So this is how the science and engineering we're going to be moving into in the complex world. So that requires system thinking, critical thinking, creativity, and exploratory mind, multidisciplinary, transdisciplinarity. So that's it. So that is, by the way, this is just a short pitch. I'm going to mention a little bit about the system science program in the next. I also have the textbook. You can just Google it, Sayama textbook. You can download the entire textbook, 500 pages for free. Thank you very much. Should I take a question or should I move on to the next presentation?
Participants, you have any questions? No, sir. You can move on with the next session.
Oh, there's a question. Yes. Yes.
Sir, you told, sir, really how to recognize a similar persons in there are similar persons in similar animals are very same, some animals are same, sir. How to recognize animals in AI, sir? Animals and the birds and the parrots, how?
Animals, you're talking about animals and their intelligence? Can you be more specific about the question? Yes. You can just come over here.
Some animals are more or less, look similar, like probably a leopard and a tiger or something like that.
Making use of this AI tool, how do we distinguish, how that distinguish between the two animals or similar kind of things or objects? Am I right?
Yes, sir.
Yeah.
How it will be recognized?
Thank you very much. Yes. So there are multiple ways to do so, and then the traditional pattern discovery approach that I mentioned, you can still use the, any kind of differences in their animal skin patterns or behaviors, etc. Right? So you can still include the multimodal signals. Could be pictures, could be audio, could be movement. So, and then you can train your machine learning algorithms. Another approach, which might be coming from the second approach I mentioned, is that because you already know there are 2 species, 3 species, and you already have a theory how they are different, right? Like a tiger and leopards, I'm not an ecologist, but if you know those animals, you know the difference, because humans are obviously able to tell the difference, right? So you can go back to those basic knowledge, and then you can go back to the observation side. If they are different in this way, at least theoretically, what kind of observational differences should be expected in the pattern or behavior, and you can specifically target those differences that are predicted by the theory itself. So that is, in my opinion, it's a much quicker way to train the machine learning instead of just trying to use the black box approach. Is that clear?
Yes, sir. Yes,
Yeah.
sir.
Thank you.
Thank you, sir.
You should understand the pattern. Understand the pattern and the behavior.
Yes.
Accordingly, you will have to train the system. That's what he's trying to say.
Okay. Yes. Could you use the microphone?
Sir, about COVID-19 in your institute, you are find on research, sir. You told that 40% is the cumulative density population, but in the same research, can we find one path so that that 40% is achieved? Only in the path, only people has to travel and people has to come out, so that that 40% is achieved with the data science.
Yeah, so that's a great point. So reducing the population size to 40% does not necessarily mean in reality that population is reduced randomly, right? So there are always correlations, and chances are that even after we reduce the population size to 40%, students might still hang out together. That's a nonlinear effect, which is missing in this simulation model, and you are absolutely right. So we didn't consider that in this particular case, but if we were to include more nonlinear effects, like a social effect, we should definitely incorporate that together. Because that's actually true. If you have a student population here, you have a party, they want to come together anyway, right? And let's reduce the population size from 100 students to 50 students. You host the same party, they come closer together anyway. It's not the reduction density. You are absolutely right. Yeah. No,
Any other
there's one
questions?
question from Dr. Chandrasekhar. Can you raise your hand? Okay, yes. Okay, the final presentation is going to be very short. How much time do I have? We need to finish it by 12:30, right? Is that so? 10 minutes? So I would like to introduce who we are. So you have already seen the mechanistic modeling, and this is the academic program I'm directing, system science. Binghamton University is part of the State University of New York system. It's one of the largest higher education system in the world. We have 64 campuses, 64. Yeah, many. And there are 4 university centers, Binghamton, Buffalo, Albany, and Stony Brook. Those are the 4 major research centers that offer advanced degrees up to PhD. And each campus competes against each other. They are good friends and rivals. We always say Binghamton is the best of the best among the 64. And we have evidences. We have the average SAT scores, that's the standardized score, Binghamton has the highest SAT score students to our campus. That's why we are best. We are also located in the place where IBM was born. Because of that, our region has a very strong industrial activity still going on. This is how the city of Binghamton looks like if you want to come over. This is the campus. Yeah, we are very happy to have a really beautiful campus. These are the pictures typically we see in the fall, like last month and early this month. There are so much beautiful fall foliages you can enjoy. By the way, this is also our university campus. It's not a picture we downloaded from Google Image. So we have a nature preserve. You can enjoy the beautiful nature, right? And we also have a Nobel Prize winner. We always brag about this. Dr. Stan Whittingham. He is a person who discovered the chemical principles of the lithium-ion battery that we are using in smartphone, laptops, all kinds of the mobile devices. He is a person who discovered that lithium-ion battery could work back in the 70s, and he won a Nobel Prize in chemistry 2 years ago. And if you ever have come to our campus, you may have a chance to take a selfie together with him. I came from a department called the System Science and Industrial Engineering. This is a fairly large department, and one of the members is our Dean, Krishnaswamy Srihari. He's actually from this university, Anna University. And together with 28 faculty members, we offer programs in system science, which is all about modeling and simulation, just like I showed you before, together with more applied industrial system engineering and healthcare systems engineering. So if you have any interest in any of those programs, I'd be happy to answer those questions. So I would like to briefly introduce this discipline, system science, and then I'm going to stop. The system science is part of the engineering, of course, but it's actually very transdisciplinary. Unlike many other academic programs that are structured based on something, such as computer science is about the computers, mechanical engineering about the mechanical properties of matter, biology about the living systems, etc. But system science can study anything, as long as you use the systems approaches. So it's based on the methodologies of research inquiries. So what are the unique features of this field? We use systems as a key concept. It's the formal representation of anything real. As long as you approach some kind of phenomena, you identify components, and you identify interaction between components, and try to understand what is going to happen in that interrelated set of components. So that's the system. Therefore, the focus area of our study is not about components alone. Instead, we intentionally try to study the effect of interaction between components. This is very different from traditional science, especially statistics. I said statistics is the core of machine learning, absolutely. But key idea of statistics is independence. If you have taken courses in statistics, you know the IID, independent and identically distributed. So that is a very useful assumption to make a mathematical treatment tractable. But in reality, everything is interrelated. So system science tries to consider exclusively that interaction as a main focus. And we consider the effect of boundaries, outside environmental effects, contextual information, how systems are going to change over time. You can be a different person tomorrow, right? So things change, properties change, and anything that we see in real life continuously evolves over time. So that kind of dynamical property is also another very important subject in this discipline. And we use math, logic, computer simulation, statistics, any kind of quantitative tools. Right? So I'm going to skip some of the things. Yeah, these are the key concepts, the topics people study in our discipline. So I'm going to skip the next few slides, but essentially, the last 3 years of COVID-19 pandemic have many people realized that systems approaches are really necessary because many of the problems we saw in pandemic came from systems properties, not necessarily medical or pharmaceutical issues. Like how to make people's behavior change, how to distribute vaccines, how to make the arrangement for the social intervention, etc. So that's all the system properties. I'm going to skip these slides. Maybe I can just show you this visualization. I said the system science is about considering interactions. What we have been doing is this kind of visualization. Let me play. And this is actually the traditional data science, not quite a system modeling, because this is not even simulation. But even in the area of data science, you can show the interaction between variables. Many of you have seen curves of the positive cases, number of deaths in COVID data, but very few people they try to visualize the interaction between variables. Let me play it one more time. Now this is showing the positive cases. Now that's delta, right? Is it delta? Probably. This might be delta. Now India got a big hit in delta, and then now you see the Omicron coming in now. Here you go. This is the Omicron. You see the wave, right? The global pandemic is not isolated in many instances, but instead there is a clear wave you can see. So this is yet another way to focus on the interaction between different variables that illustrates how the society in the world is actually like a system. So we have been visualizing this kind of stuff for the US domestic cases, as well as the global cases like this. We recently also did the similar thing with monkeypox. Many international news media picked up this visualization as a very effective way to teach people how the society can be highly interrelated. And we conduct some of research as well. By now, then you will notice that it's very useful to consider the interaction between things. So this is an example. The news media in Germany, I think this is the ZDF. Here, this is the BBC in the UK. They also use our visualization in the special program on COVID-19. They produce the Christmas lectures. It's a scientific series of the program designed for kids, and they use our visualization as the starter. So I'm going to skip all the details. We are hiring lots of people. Maybe you can consider coming to Binghamton, especially because this is a highly unique program. You can work on data science, machine learning, statistics, together with the system modeling skills that I emphasized. And our alumni went to a wide variety of career paths, not just the data science or IT. And of course, there are many alumni who went to data science areas, of course, but many others went to healthcare, industry, education, psychology, neuroscience, etc. Because of the comprehensive skills that you already have, but you just need to realize that being engineers, being computer scientists can mean that you are very skillful individuals and you can move into many different professional domains. And the system science degree can be helpful for that. Okay? We offer master's, PhD, advanced graduate certificate. We now offer programs also entirely online. So we actually have students from India, Canada, Africa, Kenya, Australia. They are studying toward their graduate degree from their home country. So this is also becoming available. Okay. I know that I'm running out of time, so let me summarize some of the details, and then I will stop. We accept students from any major, and the important thing is whether or not the applicants have the strong interest in systems approaches, just like what I illustrated here. This is a very important complementary skills to the machine learning AI. So if so, you are in. Okay. And we also have the mechanism for those who are currently in the 3-year bachelor's program, which is very popular in this country, India, and as well as the UK. If these criteria are met, we automatically consider the 3-year bachelor's degree in India as equivalent to 4-year degrees. Okay. GREs, and you can see the policy. If you want to have the departmental funding, I highly recommend you to take a GRE and submit a really good score, and then you have a higher chance to get selected for funding. Or if you don't really require funding, like making the arrangement of loans here in India and come to the United States, GRE, it can be optional. So in that case, you can just send me email to discuss the waiver. Okay. And there are many websites. I'm going to share the slides. So for those who are interested, please take a look at those resources. Many students can also get employed on campus for various roles, so you can still get a stipend while you study. Okay, so I'm going to skip most of the details here. Maybe you want to know what our alumni is doing, right? That could be the last few slides I can mention. These are the courses you can learn. One example. Students who are studying in data science in our program, System Science, they typically get a job in data science areas, especially because Binghamton is very close to Manhattan. It's just a 3-hour ride. You jump onto the highway bus, Wi-Fi equipped, you check the emails, you check the Instagram. In no time, you are standing in the middle of the Times Square. It's a very convenient place. So therefore, there is a lot of data science jobs in the financial analytics, the healthcare analytics in the Manhattan area. One successful story, Jay Sivakumar, he must be from the southern India, based on names. Yeah. He recently graduated from our system science program, getting a PhD. His first job is already the assistant VP in Citigroup, Citibank. And what makes me a little bit complex feeling is that his starting salary is much higher than mine. After 30 years of higher education experience, I'm earning less than our first-year PhD students. That's what it is right now in job market. You could do the same, because he could be, very similar. He might be able to help you finding similar jobs. Students work on the financial market prediction, psychiatric clustering, or the human idea generation studies, etc., many other studies. Other students get academic jobs. We are pretty good at producing professors, especially those who study scientific questions of complex systems. This is Dr. Sinakan Mohammadi. He's now the assistant professor in computer science at the University of Oklahoma. I'm going to skip some of the details here. And finally, the most popular, I would say, domains of study include healthcare. The healthcare is a problem in the United States. As some of you know, we spend the most to get the least. There's so much room of improvement, and many students study in this area, and after they graduate, they get a job in the healthcare domain as a data scientist or system modeler, optimizer. So there are lots of room for improvement. One last student research example I want to make. This is highly applied research. This is Dr. Ben Schleich. He obtained his PhD in system science. He worked on the system modeling of the organ donor network. Organ donor network is a coordination network. When someone passed away by accident, unfortunately, there might be a chance that the several organs can become available. You need to have a coordination mechanism to decide which organ should be sent to whom. You need to consider priorities, you need to consider age, you need to consider biological, biomedical compatibility, etc. It's a really critical coordination network. There's an organization called Live on New York, operating in the Binghamton area. Their performance was suboptimal. It was not going well. So this student actually went inside the organization. He became part of the system. He observed all the phases. He recorded everything. He studied how the decision was currently made. And he created a system model. And then explored how to change it. So this is the hypothetical scenario I keep telling. What if this? What if that? And after many iterations, he came up with much better operational protocols. Beautifully, this organization actually adapted his research as is. And then they changed the coordination mechanisms. As a result, the student research started saving more people's lives. So it's a life-saving research done by our system science majors, which makes us very proud. So I think that's it. We also have many bragging slides. We produce lots of professors and industrial professionals. Let me skip. Research centers, we also have conferences, we have journals. But anyway, the final message I want to convey is this session is all about the system science and AI and machine learning. You may consider going to AI, machine learning, system science program, Binghamton, elsewhere. But regardless of what kind of career path you want to take, as Dr. Chandrasekharan mentioned at the very beginning, things are getting more and more complex today. Probably more complex tomorrow. In your time, when you get the job, there's the international world, local world, regional world, it's going to be more complex because many factors are getting more and more interconnected because of technologies and many other issues. So this requires system thinking and the system problem-solving skills. Please be capable of considering how things interact. If you consider that, you will probably be better prepared to come up with more effective solutions than just looking at each component alone. So that's the main take-home message. With that, I'm going to close my session. Here's my contact information. Thank you very much for your attention.
Thank you very much, sir, for the informative session. Participants, any queries? Thank you, participants.
So, I have completed my N5 exam in NAT in Japanese. So, does that affect my? Does that have any good effect in my career? I'm willing to complete up to N1 in Japanese. So, will that help me in any way?
So you are talking about Japanese?
Yeah, sir.
Oh, okay.
I'm pursuing Japanese classes,
yeah.
And will it have good effect in my career?
N4 stage of Japanese, correct me
N5,
if
sir.
I'm wrong, whether N5 or 4?
N5, sir.
She had just started. You're just a
Yeah,
beginner, right?
I'm a beginner.
She is at N5 level. She was asking a question whether if she can, go up to the level of N1,
Yeah.
will there be
No,
a
sir.
good opportunity of working in Japan, if I'm right?
Oh,
or-
okay, okay.
How is that?
Is there any opportunity in Japan for AI and data science?
You know what? You have the great person to talk to. There's a Japanese instructor here. We just spoke to each other. My answer is yes. If you want to eventually consider career in Japan, knowing the language is definitely a plus, right? And to be honest, Japan needs more people from the outside country. As you know, the workforce is shrinking because of the really low birth rate. And Japan needs to open up the border and then receive more foreign workers. And another reason is that recently Google created one of the major data centers near Tokyo. So Japan, Tokyo area is going to become one of the information technology hubs for the Asian regions. So that's another reason. If you measure, for example, computer science, I guess, yeah, there will be more demand for that. By all means, talk to him.
Yeah, sure, sir.
I will add to this thing. In fact, I had a talk with one of the Japanese about 2 months back. He was making a mention that right now there are openings for about 200,000, that's about 2 lakh engineers, IT engineers. In Japan, right now the requirement is that. So what they look for is they don't look at your GPA or your knowledge and things like that. They look for only the Japanese language so that you will have a better communication. Okay, so there are a lot of opportunities in Japan in the artificial intelligence and data science area.
Yeah.
Sir, I would like to pursue my higher education. In which domain will be best for learning it? AI, ML, or DS, data science?
All of them. So my point here is that the AI, even though in my presentation, I might have sounded like I'm critical to those. No, it's not. AI, machine learning, data science, they are becoming a standard. Like reading, writing, math. You learn that all the places, right? Why? Because they are very important. Essentially, machine learning, AI, data science is extension of math. Sooner than later, everybody is studying them. So you should start early so that you have the head start. But eventually, everybody will take those. And in addition to that, maybe computer programming will also become the common knowledge for everybody. So you should study all of them. The question is, in addition to that, what else you want to do?
Yeah.
Yes.
Yes, sir. And what is cybersecurity is having a same scope as AI?
Cybersecurity is actually the much more serious application than the random AI, right? AI can be creating art. That's beautiful. But cybersecurity is a real threat in many countries for many reasons. I don't really want to mention anything political here. So there are lots of demand, probably in India as well, in Japan and the US. After all, it's a game. People playing the games, right? Compete, two or multiple competing entities trying to outcompete the other. So that is where you can apply lots of data science, machine learning, AI, for the sake of the security of the nations.
Yeah.
It's a growing research area, sadly.
Thank you, sir.
Thank you very much. Ganbatte. I spoke Japanese, by the way. Good luck.
It's time to honor our chief guest. Now I request our Dean Sir to honor the chief guest with memento as token of love and respect. Thank you, sir. Now we came to the end of the seminar. Now I request Dr. Sendil Kumar, Higher Education Coordinator from R.M.K. College of Engineering and Technology, to propose vote of thanks. Please, sir.
Good afternoon, one and all present here. I am happy to present vote of thanks for this wonderful session today. First, we would like to thank our management for giving opportunity to organize this wonderful session to these budding engineers. Next, I thank Dr. K. Chandrasekharan, Dean, R.M.K. Engineering College, to invite such an industry resource person today. Our sincere thanks to our chief guest, Professor Hiroki Sayama, for his energetic and informative session. Next, our special thanks to Professor Nagaraj for his extensive support to make this program a successful in Anna University campus. Thank you, sir. Now I would like to express our thanks and appreciation to all the participants from various institutions. We extend our thanks to the live streaming session by our technical support team. Finally, we would like to thank the entire stream of R.M.K. group of institutions who are behind the grand success of this wonderful program. Thank you one and all. Thank you.
Thank you, sir. I request all the participants to come over the dais for the photo session with the dignitaries. Please, participants.
இருக்கேன் சார்.
சார் கொஞ்சம் பேர் கீழே நிறுத்து.
Standing at the back, no, you can go down. Then only your face will be visible, right? இந்த பொண்ணா
நீங்க தான் முன்னாடி
நான் வந்து என்ன பிள்ளைங்க தெரிய மாட்டாங்க. மேம் போயிடுச்சா? மேம்
I just want to make an announcement.
Participants, please listen.
See, what this is R.M.K. institution, group of institutions, Binghamton University, Emerging Technology Seminar Series. We have given you just an exposure today. We will be following with more intense and more focused seminars in future. We will make the announcements, and then generally we will have it in offline, in-person mode in the central part of the city, apart from broadcasting it through your YouTube later. So those of you who want to interact with the eminent speakers can come and attend. Others who want to know the subject, they can audit it online. So we have made a beginning, and I hope you would make use of it. It is for you. It's a way we want to serve the student community. Thank you.
Thank you, sir. Students, you can wait back, you can collect your certificates, and then you can move for your lunch.
Participants, please be seated. I'll call out the participants by college name. First, we would like to have Hemalata, Indra Institute of Engineering and Technology. Hemalata. Next, we would like to call the participants from Tech Institute of Science and Technology. Dr. C. Rajkumar, Dr. Jayavelu, Dr. S. Ganesan,